Good morning. Anybody ever watch? Maybe I said this already, but there was this show when I was uh, like in my 20s, I guess. It was called Uncle Grandpa, and there was a character, and his like catchphrase was like "Good morning" or something like that. So, I don't know why, but that is stuck in my brain. And I do it at work. Whenever I see people in the morning at work, I always tell them good morning, but I'd be surprised if anybody understood what that was from. Today is a rainy day outside. So hopefully the lighting in here isn't too bad. I mean, looks fine on my side. Um, I'll turn this down a little bit. So don't have any updates. Oh, I had to bring my bicycle into the bike shop today. I will do that after I stream, I guess. Yeah, that's fine. I get my bike worked on. I mean, you might have seen it in older streams. It's kind of like over here. Yeah. It just needs a tune up. So, I think it's like $100. That's not too bad. I don't know if there's anything wrong with it. It's been like sitting there for a couple months, and yeah, I don't know. Just gonna bring it in just in case there's something I don't know about. And then, if it gets cooler outside, I'll be riding my bike more often. I used to ride my bike all the time when I lived with my dad. I was in a different city, but I used to bike to and from work, and that was nice. Where I live now, work is a little bit further. I think it's about probably like a half-hour bike ride to get to work. Which wouldn't be bad in the morning where it's cool, you know, but when I get off work at like noon or 1 o'clock or around that time, and the sun is like at its peak or whatever, and everything is just so hot, I don't know if I would enjoy that. But it should be getting cooler as we go into like August and September and all that. So that's all I have planned today, at least in my IRL stuff. But I'll do that after I stream. So today might be like a shorter stream, and I feel like I always say that, but today it might be true. I just want to work on the visualization that we have for this BVH thing. So I think I might be done with the implementation, at least the majority of it. And I haven't like put the code anywhere online yet, but here's the code. It's about like 350 lines or so. 326. And you know, I was thinking like this doesn't need to be the most optimized code or the best BVH implementation out there. There's already libraries for doing that. This is just for like what do you call it? Like learning it and as a resource, you know? So it should be coded in a way that facilitates like a decent visualization on the like little demo that we have here. And it shouldn't be, you know, something that's like a library, if you will. Like it's supposed to be for demonstration, right? But I think what happened was going through that article that we've been going through. I don't have it brought up yet still, but what was it called? This one here. I mean, it's not like super optimized. but I think I might have stuck to this article a little bit too tightly in writing the code. But I think it's like if you ever like studied the BVH and all this, and you've delved into it and you've spent some time with it or whatever, I feel like the code is easy enough to understand. The hardest part for me is this binning stuff, which, you know, I feel like I didn't explain very well last stream, but it is kind of like a tricky little bit of code. So everything else I feel like is pretty simple comparatively. So yeah, let me put that in the chat real quick for anybody that may be watching. I do still want to follow along with this thing so that we can get BVH that will handle like rotated geometry, or scaled, you know, applying like some kind of matrix transformation to the mesh. And maybe take a look at how do you handle more than one mesh, because right now we just have a single object in the scene. And then if that's all true and that's all working fine, maybe tweaking it so that it will be like a BVH mesh, and you pass in the geometry and the material, and this is how you use it. And then this gives you back something that extends from mesh. That's how the 3 BVH library does it. I think it's called Mesh BVH. Like if you take a look at their API, you can do it 2 ways. You can modify the prototype of mesh, or the raycast, to use this accelerated raycast. That means anytime you instantiate, you know, a normal mesh, it will now use this accelerated raycast instead of the default. Or I think there's one where you can create a object maybe, I don't know. But yeah, it's putting properties on the geometry. So this doesn't typically exist on geometry. And neither does this. But it's modifying, yeah. So this doesn't exist, but you're like, you know, just as a JavaScript, you can just attach properties to anything. So I kind of want to build an API like that, where you treat it like a normal mesh, but it would extend from mesh, and then you can use it anywhere that you can use, you know, a Three.js object or a Three.js mesh, including like raycasting and stuff. So this isn't typically how you would raycast with the Three.js raycaster. You would make a call to, we call it this thing here where you got your raycaster. You would do raycaster.intersect object, and then here you'd pass in the BVH mesh, and then it would look into that object, and you know, it's got a raycast function on it, and that's what it would call in order to do this. So that would mean, you know, overriding whatever this default raycast function is doing, and it would do this part of it here where we check for intersection, this whole big function. But before I do that, I think it would be nice to clean up the visualization a little bit. So at the moment, we just kind of show like what triangle you're hovering over, but you don't get any kind of like sense of the like what's actually happening, I guess. And we have this little toggle that shows you all the leaf nodes of the BVH tree. But again, this is kind of a lot of information, and this is just kind of for debugging as I was building it, because this looks correct, right? It's a highly symmetric object, like in every axes. So you should get when you display all your leaf nodes like this, you should see something that kind of, you know, looks like it's overlaid on top of the sphere. But I don't think this is very helpful. I think it would be nice to, you know, shoot a ray into the scene, which we are doing when we mouse over the scene, and then kind of, you know, follow along in this intersect function. We take a look at like, okay, we found the node where we intersected a triangle. We can trace that back to the root and show you the path that the algorithm took, or the intersection function took, to get there. And a really easy way to do that is to add to this BVH node class a pointer to its parent. And a pointer will just be an index into the nodes array. So we have this like global nodes array. And every node that is an internal node has a pointer to its left child, and then its right child is just that index plus 1. But there's no way to go from child up to parent. You kind of lose that information as you go into the, you know, as you traverse into the tree. But it would be really simple just to add a parent index. Semicolon. So now we can like take a look at a child and then go back up to its parent. Now we're going to go all the way back up to the root of the tree. And what we're going to do is draw a box for every, like we're going to get a path from that leaf node back up to the root, and we'll draw a box for every single like node that we touch along the way. So the first thing we need is a pointer or an index to the parent node, and then down here where we kind of like modify the properties of the children, we also need to set its parent node. So you would do left.parent, or sorry, its parent index. We're not using like the actual node object, which we could. It would just be a reference to that node, but I think storing the index makes more sense. If I'm not mistaken, that's usually how they do it when you want to, we don't really rearrange anything, but in like game development, I think they do this technique a lot where they don't store a reference to the object because that reference could get stale. Like the reference, I guess the reference is different than the pointer. So if you don't store a pointer to the object in memory because that memory could be modified. Instead, you store a pointer to the location in the array that that object is supposed to be occupying. That might be a little bit unrelated, but I think that's a good technique, and we're going to follow it here as well, where we're just passing around indices. And the nodes array doesn't really change, where we allocate like all the nodes that we could possibly have. Up here, right here, all we're doing is just like modifying information or data about each node. So what we need to do is when we modify the left and right children, we actually need to modify now its parent index. And we don't have the node index, but we can pass it into the function at the top. We'll do that, and then down here we'll also do it for the right. But this node index we don't have. But we do have the node, so at the moment it's just passing in the node. Where is it? This is the giant function. Rather than passing in the node, we could just pass in the node index. And then to get the node, you would just take a look at nodes and then get it at the node index. So that's kind of the same thing. But now we have the node index and we can pass it along to the children down there like we did. But now this needs to be updated, and this will be left child index and right child index. And then at the top, yeah, like where we create it here in this split function. So this is inside of create. The root index is 0. So we could just pass in 0 right here and it would work. See, like that's still the same thing. But I kind of don't like, I mean, I guess it's not too bad here. Just passing in like a 0 here kind of feels, I mean, it makes sense. At the very top or at the start of the array is the root node, but I don't like just passing in like magic numbers like this. So what I want is to just store it in a variable. And that kind of keeps those two in sync, right? Index. I meant root index. So now every child has a way to get back to its parent. So the idea here is that as we intersect, or we check for intersection, right here, we're pushing in an index into this. Yeah, I did change this off stream, so let me explain what's happening here. Rather than push like the triangle that we intersect here, I think that's what we were doing before. We're pushing an index into, yeah, this is the triangle index, so maybe we'll call it triangle index. Oops. In here, you change this to triangle index. And then when we use this thing in the actual component, we'll get the triangle index out here. And that'll be triangle index. Yeah, so we get out the triangle index, and it's really simple to test that the triangle index is different than the previous closest triangle index. What this is doing is making sure that we're not running all this code if the intersected triangle hasn't changed. So if I get real close and I just mouse over this little thing, it's returning the same triangle every time. So there's no need to set the line geometry points and all this, because nothing's changed. And I want to make one little other change to this. I finally found out what this does. This backface culling. So that will, as you enter, like you shot a ray into the scene, we're intersecting with this triangle here. But we also intersect with a triangle on the backside. But if backface culling is turned off, then it won't consider that an intersection. And you can see if you take a look at the length of the intersections array. Where is it? Yeah, right here. With the backface culling turned off, let me put this on the bottom. Oh wait, it's either on or off, I forget. Let's set this to true. So there's like right here, let me clear this. As we intersect, we only ever have one object in the array, and that's the first intersection as the ray enters the sphere. If we want the one where it exits the sphere, then we have to turn this to false. And now we should get a length of 2 every time. Um, right now we're only kind of concerned with the first intersection. So I don't know. It doesn't really hurt to leave this as false. But if you had a geometry where you had like a whole lot of intersections, but you only cared about the first, then you might want to set this to true. But in that case, as soon as you saw an intersection, you would exit this for loop. You would probably exit the whole intersect function here, like you would return early if all you cared about was the first intersection. So yeah, I'm gonna leave it as false so we get both intersections. And then when we come over here and we, look at every intersection, we'll just get the closest one. So we really don't need every intersection the way that we're visualizing this, but I'm just going to leave it like it is. So now that we have the triangle index, we also have the node. No, we don't, not yet. Let's add that. So in this intersection, we return the triangle index, which tells you what triangle you intersected with, but now we can also return the node index. The node index will tell you what node those triangles live in. But node index is not part of this type, so let's add it. And that's just index into the nodes array. And we get the node index. It's passed along here. So we already have the node index. Let's look at how this thing is getting called. Oh yeah. So it's a default. Like a default's to 0, and 0 is the root index. So, like, it might make sense again to move that root to a constant, like this. Now, where do we use root index? The node index is the root index. So if we don't pass this in, we're always like checking from the root. Yeah, and then we just pass the node index along. Oh, okay. So right here, when we get the node index out, yeah, okay, I see now. I remember how this works. So if we had an intersection, we pass along that node index, but now because the node index contains a pointer back to its parent, we can trace that back up to the top of the tree, right? So now if we look at the intersections, and we just look at one of these, yeah, it's got a node index, and then if we want to trace that back up, let's make a path for this. And this will just be a list of numbers. Let's do it down here where we know that something's changed. And I just remembered some other thing I wanted to modify too. So here, where we check if the triangle index or triangle count is greater than 0, this is telling us that this is a leaf node, which means that it contains triangles because triangle count is greater than 0. We actually don't have to do this check because let me just put this in. If triangle count is less than 1, I think that's how that works. Yeah, so here we had that if statement. We don't need to do that because if triangle count is 0, this loop will not run because I is not less than 0 and I starts out at 0. So that's a little bit of an optimization, I guess, a very small one, but there's no like, you know, there's no for else, which would be nice in JavaScript, I guess, but we can just kind of simulate that with this check here. So we skipped over this loop if we had a triangle count that was greater than 0. And we want to enter this branch if the triangle count probably should be like this. It's equal to 0, but I'm just going to do less than 1. Could be the same result. Yeah, that's a little tiny little optimization, I guess. Okay, so we have our path. Then what we can do here is we'll get the node index out. And then we'll enter a while loop. We'll say while the node index is not equal to 0. We want to go all the way back up to the root. So while it's not equal to 0, what do we need to do? We need to get the node. That will be nodes at node index. And then the parent index is node.parent index. But we want to push in the node index. And then the node index becomes the parent. So we could just put this here. When we don't have that node index, oh yeah, we do. We can just set this to let, and then node index will now be something that can be modified. So we do that. Now let's take a look at the path. And then, yeah, so right here. So this is where we started. And then we went all the way back up to the node, to the root. We don't have 0, but we can include 0. I'm not sure if I want to. Yeah, I probably should. Because we always, like in reality, we always check the root. So let's see. Take a look at node index after this loop. Yeah, it's equal to 0. So we want to push that into the path array as well. But there should be a way to do this inside of the loop. We could do it. Maybe we could do a do while? I don't know. Because if we visualize these boxes, or like these nodes now, we won't include the root index. And we can also, I mean, a really dumb, simple way is just to push in whatever, you know, this is equal to 0 now. But I'd like to do that inside of the loop somehow, and I know I've done it, but I can't remember how I did it. Yeah, what happens if we use a do while? Oh, you know what? Oh, I remember now. Yeah, so this root, or this parent index, it is -1 if it is the root. And the index, right, should always be positive, but if you are the root, you do not have a parent. So we can take advantage of the fact that JavaScript numbers are like, well, I guess they're like 64-bit doubles or something like that. So we can store negative numbers here. We don't have to worry about like unsigned numbers here. So we can take advantage of that and set it equal to -1. And then now what we can do is, if the node index, or while the node index is not equal to -1, let's see if that gets us where we want it to be. Okay, yeah, there's the 0. So the 0 on the, right here. And then, I guess we could do this too. I always like to do these, I don't know why, but I prefer using like these kind of comparisons over like strict equals or not equals. So this should be the same result. If we look at path, at path.length, -1. So we should see a 0 at the end. Oh. We have undefined. Oh, this should be greater than -1, right? Yeah, so the check to see if you are the root is if your node index is not, or if it is equal to -1, then you are the root. So maybe we should do it like that. But then again, like, you know, you'd want this to be in sync with the other variable. Like, you know, having -1 in 2 spots doesn't feel right. So let's do it over here, root. Okay, is that correct? Yeah, that's good. Okay, now we have the path. Now we can traverse over this path and create boxes. So that'll be pretty easy. And I'm going to use a, you know, I'm not going to do the for of loop. I'm just going to use the indices because you'll see in a moment how we're going to color these things. Alright, yeah, let's just do the for of for now and then we'll change it in a second. So for index of path, let's make a box. Or we have the box, that's the actual node. So we'll do node equals nodes, the index. And then we'll do const helper equals new box 3 helper. We'll pass in that node. And I'm going to add this to a group. I think we already have the group. Yeah, right here. I'm going to get rid of this. And let's move down that group. It doesn't have a very good name. It's just called group, I think. Yeah, right here. So let's take all this and we'll put it down here. We'll let it be visible. Change it to boxes. So, where is it? We'll do boxes.add helper. And that should add the boxes to that group. So now, right now the group is empty, but as we go, we're keep adding boxes to that group. We need to clear it out. So before we do this loop of adding, we'll do boxes.clear, and that will remove them. But it won't remove them from the GPU. So what you have to do is dispose of every box. And you could loop over, like before you do the clear, you could do like child of boxes.children. And then, do child.dispose. Could do that, but when a child gets removed from its parent, it has an event for that. So you can actually add an event listener. Oops. To the helper. You could do helper.add event listener, and it has this removed event that you can listen to. And you get out the event, and then this event has a target. And it is actually the box 3 helper right here. So when it gets removed from the group, we can then dispose of it. Like that. And then to see that this is actually working, let's just console.log removed. So as I mouse over this box, if I change the triangle that we intersect with, then we should see that remove getting logged. Assuming, because it's getting removed, it should be running this callback function. So that means that this is running this code as well, so it should be disposing of the resources on the GPU. And this helper object, its parent is only ever going to be that boxes group right here. So now as we mouse over this thing, we can see like what boxes we checked. And if I get a little bit closer, you could see like to get to this triangle, you tested the big box. We do one on the side so it's easy to see. So to get to that, I'm gonna try to like point it out. It's like right here. Follow like an imaginary line like right here to that triangle. To get to that white triangle, you tested, this box that contained everything. Did I intersect with that? If I did, then I can split that box. Well, this happens when you create the BVH, but you can tell that, like, if I take a look at a triangle on this side, on the right side of the sphere, I didn't traverse down that side at all. And then, if I move over here, I don't traverse down the left side at all. And, same thing here. This is like the top right part of the sphere. I don't traverse down the bottom at all. So, like, every time that you, like, jump into a node, you're cutting off, like, half of the search space, I guess. You're splitting it up into two, a left and a right. And then to get like kind of an idea of how many intersection tests you did, so every box here should contain just two nodes, or I'm sorry, two triangles. And I don't have a good explanation why, but it comes down to how this cost function is being compared. So if you look at like best cost, or what did I call it? Min cost. I think I might have talked about this like a few streams ago, but you get to a point where splitting up the node isn't going to help you at all. Oh, you read a Raycaster too? Or a Ray Tracer? Yeah, it's pretty interesting. Uh, kind of difficult if you're not used to this kind of code. Um, and you know, I took a look at this library called mtree, I think. Yeah, this Intel library. So this, I guess, is built for Intel CPUs or like GPUs and stuff. Oh, nearest neighbor approach. Yeah, I think there's different ways. Like it depends on how your mesh is set up. Um, so in Three.js, like everything is just a bunch of triangles. That's all you have. And if your like mesh representation is different than that, then you know doing like the way that I'm doing it here, which you know just loops over triangles a bunch of times in different ways. Yeah, I think there's like better ways to do it if you have a different representation of your mesh, but like from what I can tell, most of the time you're just working with triangle data, right? Um, but yeah, I was looking at other like implementations of this. This mtree library is very sophisticated. Like this is the most complex code I've ever seen. Pick the closest triangle, group them, and move outwards. Yeah, there's a bottom-up approach and a top-down approach from what I've read. Um, yeah, and then we use a stack too in the intersection code down here. Where is it? Yeah, we keep a stack, and as we like, oh, we could parallelize it. That's cool. Yeah, and there's an article we've been following along. Do I have it? Yeah, right here. Where you do, yeah, ray tracing on the GPU. I haven't reached this part of the article yet. But yeah, like I don't think you use, you know, a shader. You use like a general purpose. Well, I mean, you use a shader, but you don't use like a graphics shader, if you will, right? You use like a compute shader to do it, and you can split it up so that you do work like parallel or like concurrently or whatever, right? Um, and it should be highly parallelized because if you are doing a ray tracer, right, you can take a look at every single ray individually. Um, you know, one ray doesn't affect another ray, right? They're independent. Um, but I wonder if they can do the like construction of this thing on the GPU. Yeah, that's what I've read. Is that once you have the BVH set up, uh, like interacting with it, you know, shooting rays and scene and all this is very fast, but the construction of it is what takes a long time. And there's like algorithms for doing it very quickly, and I guess you can do it on the GPU, but I haven't. That's like a bunch of like white papers that I came across were talking about that. You can do anything. You do your taxes on the GPU. What's it doing? Yeah, that M tree library. Uh, like I guess they, you know, it's built for Intel hardware, so they do a lot with like kernel stuff or you know like very specific hardware-based functions and you know definitions and stuff like this. Um, yeah, yeah, yeah. But I was just building one just to see like how it worked and everything. Kind of like you know you get like this interest and you're like, how does this thing work? Let me see if I can make it myself. Yeah, yeah, I think NVIDIA has like probably, you know, BVH stuff built into their GPUs and stuff. And, you know, you probably just import CUDA or whatever. I don't know exactly how you do this, but it probably has like a BVH library for you to use, and everybody's got an NVIDIA graphics card, so you're probably okay to use that, right? You're like if you're building it for, you know, the web or for like a mobile app or something, you probably couldn't use. Well, maybe, I don't know. But if you're building a game, right, I think CUDA is a safe bet. But also, if you're building a game and you're building it with an engine, right, that engine probably has a BVH library for you to use, or it's like built in, and you know it's tucked away behind some library code that you really don't have to understand, with a nice like API behind it. So this is our traversal to get to that triangle. Yeah. Yeah, from what I can tell, people are using BVH mostly for ray tracing. But I kind of wanted it to be, like, my use case is for ray casting. And the idea I want to do is recreate this little demo. What is it called? BVH? Yeah, it's right here. I don't remember the name of it. It's got like yeah, this one here. So everybody's been playing that Mecha Chameleon game. I don't know if they're still playing it, but it was popular, you know, a couple weeks ago. They probably still are playing it. But in that game, like, you can paint your character's body and all this. So I wanted to recreate a demo like this, but rather than like just using this library to do it, I wanted to make my own little BVH just to see how it was done. I think you can control the size of this, yeah. Oh, it's got the... Look at that. I could do it on mouse scroll too. That's cool. But oh yeah, I remember what I was saying now. So the cost of getting to this triangle here is the length of the path. Well, I don't think that's correct, 100% correct, because you are still checking intersection with the left and the right child. But you can imagine the only two triangles that you tested for was the triangles in the leaf node. So rather than testing all the triangles for the entire mesh, which is like 980 or something in this case, you're only testing two triangles, and then you're testing, you know, all the nodes to get down to the leaf node. Which happens right here. And that should be a lot faster in theory than just, you know, checking every triangle for intersection. But I kind of want to put that to the test just so that we have some, you know, sense of how much like more performant this is. But I haven't thought of a way to do that yet. But let's move on with like cleaning up this visualization. So here we have the boxes. What I want to do is give a different color to each of these boxes. So as we go down and the boxes become smaller and smaller, we can change the color of them. And that's why we'll change this to be a let I equal 0 kind of loop. Alright, let's just do L. I'll put it outside of here. So I is less than L, I plus equals 1. L is going to be the length of the path array. And then we'll make a... I don't know what to call this, but I'm just going to call it A for now. That's going to be 1 over the path length. So this is actually just like the reciprocal of L, I guess, but we'll call it A. And then this has to be L. We can do that. So here we get the index. Oops. That's going to be path at I, and then this is index. Oh, and I need to name this something else. Let's call it like M. That's because A is like it would shadow A here, and A is the triangle, one of the vertices of the triangle that we're intersecting with. So this should be the same. And then that M, we'll multiply it with the I here, so we'll get like, we're going to use HSL, so we'll do U is equal to I times N, and I is constant, so let's do it like this. I'm going to put this down here, so we'll make a color. We'll set HSL. This will be the hue. Saturation, we'll just do 1 fully saturated. And the lightness, I want that to also be, it'll be closer to black, I guess, if you are further out, if you're a larger box. So it might be hue or it might be something else. Oh yeah, we need to use it. It might be 1 minus hue, but let's see. So let's try 1 minus hue. Yeah, so it's kind of hard to tell because we have boxes that are overlapping each other, but like the left box, this one here, should be a little bit darker. And as you go deeper and deeper, the boxes become more and more light. Maybe we could do the saturation. I wonder if this just gives us the same color. Yeah, I think you have to set this to be something different. I don't know. We need to test like what the best way to color these boxes is, because it's pretty noisy in here. And you could change like the opacity of these lines, but it's coming from this helper, so you would have to like do something like helper dot I don't know how to get to this helper's like material. We can take a look at the docs. Or I guess the source code. Okay, so yeah, it has the geometry. Where's its material? Oh, it's a yeah, this like line segment. So here's its material. And I guess we could set its opacity. We have to also have to set its transparency. And you know, materials, because this is like an object 3D or whatever, you have to test that this material is not an array, which is kind of annoying. Because it could have material groups, and that means like, you know, for this part of the geometry, use this material, for this other part, use a different material. Do I want to bother with all that? I don't think so. At least maybe not on stream. Where is it? Yeah, let's at least darken or like add transparency to the mesh material. So here we can do transparent, true, and then like 0.1, I guess. Maybe even darker than that. Like you can still see. I don't know, that's pretty That's pretty dark. Yeah, and this should still work if we turn it off. Now we only see the triangle. Oh, this looks cool. I don't know. But I thought about, if we have some like stats or something here. So it's easy, it's really easy to tell like how many triangles he checked for intersection right here. You would just push in, every time you did this call, you would just push, like, not push, but you would add to like a triangle test number. So like, let's say you had triangle tested tests count or something, and every time you made this function call, you would, increment triangle test count. But that should also be equal to the triangle count here, because you're looping over triangles, so you could even do this. And then if we return this as like part of the return function, or like as part of the thing that we're returning, does intersections get cleared? I gotta make sure we're clearing intersections. Oh, we are, because it creates a new array every time. And where we make that call, here, where's the, yeah, right here, we don't pass in the, well, we don't pass the node index and we don't pass in the intersection. So it is making a new array every time, which is fine. Yeah, so we have the triangle count, and then we're triangles tested. We can return that over here. What is it called? Triangles tested. Then we can get that out here. Oh, this needs to be an array. Or we can destructure it here, and then we'll do triangle count. Let's see how many triangles we tested. Okay, so yeah, it just tests 4 triangles, it looks like. Sometimes it tests 6 or something. I think that's correct. Let's see if we add... Yeah, so we only ever... So this should be 0 if the node is not a leaf node. So we're just adding 0 to the triangle count. To this number here. Doesn't change it. So I think that's correct. And then down here, when we check the intersection of the 2 boxes, let's do alright, we check left and right, so we should just add 2 to that number. And it's any time that we make this function call. And we can return that as well. So you can imagine, right? If you were writing this as like a library, you wouldn't keep track of all this information. This is just for helping get a sense of, you know, how much more efficient the BVH is than just checking all the triangles. But yeah, like in the real world, you would not keep track of this, I guess. Or you'd write a separate function or something to do some kind of tracing. Now let's take a look at both of these values. So, node. Okay, so to get to the where we are now, we checked 32 nodes and 4 triangles. Now is that faster than checking every triangle? I'm gonna assume it is. For now. To really check if that is faster, you'd have to, you know, take a look at the frame rate, I guess. I think that's what you would do. Or, you know, you could do this where you find a mesh with a ton of triangles in it. And then, you know, you'd have one test where you didn't do any BVH, see how slow it is, and then one test where you did. Now, that wouldn't give you an idea of how much faster it is, I guess, but if it was faster, if it didn't, like, lag or anything, then you knew that, like, maybe this BVH is worth it, right? But I think I might play around with that later on. And I don't really like keeping these, so I'm gonna get rid of these. I might think of a better way to do that. Oh, what happened? Yeah, but it's really nice so you can see like what's happening here. Let's try some different geometries. So our geometries have to be indexed. This is only working for indexed geometry at the moment. But I think most of the Three.js primitive geometries are indexed. Where's our geometry? Oh, we're in the wrong file, that's why. So let's try this one, I guess. I mean, I know these will work, but I just want to see what they look like. Do we have any more interesting geometries? I cannot spell. There. And I don't know which of these are indexed and which aren't. Okay, yeah, we have a check here for that. So, if one is not indexed, we'll hit this error, which is going to prevent us from doing anything. So, I think we're okay. So most of these are like symmetric. It would be nice to get a model in here that you know, we load as like a GLTF and try it out on that. Let's jump over to one of the other demos, like this one. And I don't remember if this one is indexed or not. where do we actually use the car? Yeah, when we load cars, we get the cars out. Yeah, it's a GLTF array, so let's do car dot, we'll do, yeah, for every car, let's do car dot geometry dot get index. Can I do that? And this is under PS1. Oh, okay, so this is a scene, right? Yeah. So we need to get the geometry. So it's like scene dot I don't know if I want to do it this way. Oh, we do like car dot scene dot traverse. If is mesh oh yeah, so if it is a mesh, then it should have a geometry. Okay, so it looks like it is indexed because we got a buffer attribute out here. So this will return null, I believe, if it's not indexed. So we should be able to load up one of these cars and pass it along and test it out on an actual like model or like a GLTF, right? So let's get rid of this. We'll go like earlier, maybe 20 minutes. How do we load this? I don't even remember. But what's nice is that we can steal code. So, anybody have any preference for which one we take? We have a van, a wagon, a sedan, a saloon car, which sounds pretty cool. Maybe let's do saloon. I think that the saloon is the like police car looking one. Maybe we'll take sedan. That should be like generic enough. Oh, yeah, we... let's see. We need this. Need to import that. And this has to be done inside an effect so that you don't try to load it server side. So effects always run, you know, on the client. Oh, this just means that we have to do everything like asynchronously. Which means we create like the BVH after the GLTF is loaded and all that. Let me do this. I want to make a commit before we do all this. That way if I need to roll back, then I can. So let's commit this. Oh wow, I made a bunch of changes. What did I delete? We'll add this, why not? And we'll add that. We'll add BVH demo. I don't know. Do I want to continue this? I kind of want to go get my bike in the shop. So, maybe this will be what we start out with on Thursday's stream. Or, sorry, on Tuesday's stream. So yeah, it's going to be a shorter stream today, so that checks out. Let's pull this back up. So, next stream, what I want to do maybe is load up a GLTF model, and I might find a model that has more triangles. Those car models are pretty low poly. Because we were using them for creating that PlayStation 1 style graphics. So I might look for something that is more complex. And we could probably even test this with that dragon mesh that everybody uses. What the heck? I want the... Isn't it like Stanford Dragon Mesh or something? I don't know, it's this one here, but I don't know if it's called the Stanford Dragon. But I think the original model has like 800,000 triangles or something crazy. Oh, that's funny. Somebody made it like a Yoshi mesh. So yeah, we might try it with that. I might have to simplify the dragon. You know, we'll see if we can find different versions of that dragon. After that, what did I say I wanted to do? Yeah, maybe we'll start working on like painting this thing. Oh, that's what I wanted to do. So we have this isn't set up in such a way that like the other raycast functions are set up. If you take a look at like, let's just call it raycast. I guess I could just log this. Yeah, so this has a raycast function that does a bunch of stuff. This is cutting it off too. What I want to do is overwrite this raycast function for this BVH like mesh, and the way that you would utilize this is you'd be like BVH mesh equals a new BVH mesh, and you would pass in the geometry and the material. And now, whenever you try to do like raycaster dot intersect object, you pass in the BVH mesh, it would return the stuff that this thing is supposed to return. So this has a specific like signature on it. And if you take a look at that here, let's do intersect object. It has this as the return type, and there's information on here, and one of them is like the face of the mesh in the index here. So you could use this information to do like vertex coloring, where you would, you know, this material that this mesh is going to use vertex colors, and on intersection you like update the vertex color buffers. That's how they're doing that painting demo over here. So that's kind of what I want to work towards. but I have to think about how we're going to translate this into that like raycast. You know, we'll have a raycast method here that we overwrite. Need to think about how to do that. Because it does a lot with like material information, and we might do, I think what we'll probably end up doing is a version of it that is not 100% like complete, I guess. It will only handle like specific materials and stuff like that. We'll see how it goes. So that's what I'm going to think about. And that probably will happen on Tuesday. So, I'm going to go take my bike to the shop. And it's not raining at the moment, so now's a good time to go. And then get some lunch. And then I will probably be playing some Ace Attorney, or maybe I'll be watching a stream or something. So if anybody's still hanging out, thanks for stopping by. Here I am. Here's our opening scene, but I need to change to the thank you scene. So thanks for hanging out, thanks for chatting, and I will see you guys on Tuesday. Adios.